Suppose y is equal to f of kl is the production function of the firm, and k and l are the inputs. Suppose r is the unit price of capital, and w be the unit price of labor. Okay, so the cost of production is of course given by C equals to WL plus RK. This is the cost of production, and you want to find out that how much of K and L the firm has to employ so that cost is minimized and it has to produce, say, Y bar units of output. Fine. So the firm wants to know the minimum cost to produce Y bar units of output. When I say minimum cost, what are the endogenous variable here in this objective function? So L and K is something which the firm can choose because W and R are given exogenously to the firm. So what does it do is that it forms the Lagrange. Objective function is WL plus RK subject to this constraint. The constraint is that you have to produce Y bar units of output minus f of kl. Okay, so the first order conditions are del L by del L is W minus lambda f of L equals to 0. Del L by del K is R minus lambda f of k equals to 0, and the last one is with respect to constraint del L by del lambda is Y bar minus f of kl equals to 0. These are the three necessary conditions. So 1, 2 and 3. So from first and second you'll be getting W equals to lambda FL and R equals to lambda Fk. So dividing first by second, what you'll be getting is W by R equals to FL by Fk. This is what you'll be getting. Now what do you need to find out is that at equilibrium this equality has to be maintained. Okay, and of course using this condition and the last condition, you can find out the values of k, l and lambda. Now the point is that you have to check whether the second order conditions are also satisfied. For the second order conditions, what do you have to do? What is the constraint here? Constraint is the production function. Okay, so constraint is y is equal to f of kl. In fact, y bar equals to f of kl. So, and you remember this, that the bordered Hessian is 0, G, not G, here we have taken it as an F. So what you should be writing is that f of k, f of l, f of k, f of l, and then you will have to differentiate this first order necessary condition, one with respect to L. So you'll be getting minus lambda f of LL, and then with respect to K, which is minus lambda f of LK. Then this second order condition first with respect to L, which is minus lambda f of KL, and then with respect to K again, which is minus lambda f of LL. So this one is the matrix, and you have to solve the determinant for this. So you'll be solving the highest order determinant for this. The highest order in this case is H2. Okay, that is H2B. So what you'll be doing is, an H2B will come out in case if you just expand it along the first row. You'll be getting lambda FL square into FKK minus 2 lambda FK FL FKL plus lambda FK square FLL. Now the point is that in case if at this condition the cost is at its minimum, then this H2, this determinant has to be negative. This is H2B has to be negative. And what is lambda? Lambda is nothing but the marginal cost here, and since this is greater than 0, we'll assume this. So what you will have basically is F square L FKK minus 2 FK minus 2 FK FL FKL plus F square K FLL. Okay, so marginal product is positive, fine, but and the square of this has to be positive, so this is greater than 0. FKK will be less than 0, diminishing marginal product. FK is greater than 0, FLL is greater than 0, 2 is greater than 0. We'll assume that FKL is less than 0. Okay, so sorry, FKL is greater than 0. That is in case if, say for example, computer and human beings. Okay, so in case if you give these humans more computer, then their productivity will increase. So that is cross partial derivative, that is across marginal products, they are positive. But with minus, all of this has become negative. This has become negative. This is positive. Fk is positive, so f square k is positive. And FLL is negative because of diminishing marginal productivity. So the entire thing is negative. So this is negative. And hence H2B is negative. So it means that this is indeed the point of minima.